The topic of the video is spin angular momentum operator. Besides orbital angular momentum, the fundamental particles have also got spin angular momentum. And this actually was supported by Stern-Gerlach experiment. The spin angular momentum is denoted as S bar with hat, and the spin state of a particle or a system is represented by two quantum numbers s and m sub s, and the particles with a spin as a one half, half integer, are actually known as fermions, and the particles with s as integer are known as bosons. Next in the discussion is a bit of theory of spin. If the spin angular momentum is expressed as sx, sy, sz as the components, then we should expect the commutator of sx, sy as ih cut into sz, and sy as z commutator will be ih cut into sx, and then sz, sx will be ih cut into sy, and s square with sz should be giving you 0 as answer. Since uh, s square and sz are actually kind of commuting, we can expect simultaneous eigenfunctions for these operators, and if you take that as ket s ems, then eigenvalue equations can be written for s square as s square operator acting on this state s into ms is giving you s into s plus 1 as eigen value, and then same eigen function. And then for z operator, when it acts on the eigenket sms, it is giving you eigenvalue ms and then same eigenket. And if you define s plus operator as sx plus isy, and then s minus operator as sx minus isy, as kind of lowering and raising and lowering operators respectively, then if these s plus operates on the eigen, on the ket sms, it should be giving you this factor, and then the ket state is actually kind of raised to s comma ems plus 1. And when s minus operates on same kind of ket, it actually kind of loads the ket by 1. ms is actually kind of lowered by 1. Next in the discussion is the Pauli's matrices. For a spin half system, this S operator can be written as h cut by 2 into sigma, where sigma is actually expressed in terms of its components sigma x, sigma y, and sigma z, which are actually called the Pauli's matrices, and they are defined like sigma x is equals to 0 1 1 0, and sigma y is 0 minus I 0, and sigma z is 1 0 0 minus 1. Properties of Pauli's matrices. First property is together with the identity operator I, the Pauli's matrices actually form a complete basis set for 2 by 2 matrices. That means any 2 by 2 matrix can be written as a linear combination of sigma x, sigma y, sigma z, and identity operator I. Second property. The trace of a matrix, of a square matrix, is defined as a summation of all diagonal elements. And if you actually kind of compute the trace of all these sigma x, sigma y, and sigma z, for any of these things, it will be 0. Determinant of a square matrix is defined as AD minus BC. You know it, right? ABCD matrix. For ABCD matrix, it will be AD minus BC. And if you actually find out the determinant of any of these sigma matrices, it will be minus 1. And if you actually kind of compute the Hermitian conjugate of any of the sigma matrices, we see that the Hermitian conjugate will give you same answer as the original matrices. That means if you take sigma x dagger, it will be sigma x again, and then same thing is the case for other matrices. So therefore we can say that any of the sigma matrices is actually Hermitian operator. And if you find out the inverse of all these I mean any of these matrices, then you get it themselves as the answers. So we can write sigma x inverse is equals to sigma x dagger, and similar kind of expressions for sigma y and sigma z. So therefore we can say that all these sigma x, sigma y and sigma z, they are unitary operators. Sixth property is eigenvalues of sigma x or sigma y or sigma z will be plus or minus 1. And for the case of sigma x matrix, for plus 1 eigenvalue, eigenfunction will be 1 over square root 2 into 1 1, and for minus 1 eigenvalue, the eigenfunction is 1 over square root 2 into 1 minus 1. And for sigma y, for plus 1 it is 1 over square root 2 into 1 I, and for minus 1 eigenvalue it will be 1 over square root 2 into 1 minus I. And for sigma z, we can take the eigen function for eigenvalue plus 1 as 1 0, and then for minus 1 eigenvalue it can be taken as 0 1. And the 10th property is that if you actually compute the commutators like sigma x and sigma y commutator, you will get 2i sigma z, and same kind of answer for other combinations. That's it in this video, and thanks for watching.